Welcome. This is the sixth video, or this is the sixth page of notes, and in this video we're going to discuss the quota rule and one paradox that comes up from the Hamilton apportionment method. And what we're doing at this point is we're building ways to critique the different apportionment methods. So the quota rule will be something we hope applies to the apportionment method that we choose. And the paradox that we'll look at later, called the Alabama paradox, will be something that we hope our apportionment method can avoid. And so with that, we should go and just discuss them individually. So the quota rule is an interest in having an apportionment method always give a state its standard quota, either rounded up or rounded down. So this is like when you do the proportional method of handing out the indivisible objects, that's called the standard quota. And what the quota rule says is, well, you should either go up or down, but no further than that. So let's look at it with an example. So we have some country, the population is 12.5 million, it's split between the 6 states, and we are apportioning out 250 seats. So the way this table reads is the columns communicate an individual state. We have the name of the state, we have the population of that individual state, the standard quota, and the apportionment under two different methods, Hamilton's and Adams's method. So we see state A has 1.6 million out of the total 12.5 million. We see if state A was getting a perfect apportionment, so this is like the proportional kind of division of the 250 seats, then A would get 32.92 seats. And what the quota rule is saying is, okay, well, A should only get 32 seats, or they should get 33 seats, and just those two. In this case, both Hamilton's and Adams give state A 33. Let's look at another one. Let's look at C first. We'll come back to B. C has a small population, 154,000, a small relative to the total. So they would, under perfect proportional system, they would be given 3.08 seats. The quota rule says 3 or 4. One, just either rounding that number up or down. And that is what fair would be. Both Hamilton's and Adams' apportionment give different numbers, but they're both following the quota rule, because it's 3.08 rounded down or 3.08 rounded up. Now let's look at state B. State B's standard quota is 138.72. So 138 or 139 are the two apportionments that would follow the quota rule. And Hamilton's gives 139, while Adams gives 137. So that's a violation of the quota rule. This is a violation of the quota rule. Because state B gets fewer than the standard quota, rounded up or down. Right? And the reason why it seems like a violation or this is a bad thing is because we want to give all the states the proportional amount. We want to, but we can't because the objects we are distributing are indivisible. So the closest two numbers to 138.72 would be 138 or 139. So those are your kind of best bets. That's what you would like to have to choose between. But Adams' method, in this case, gives 137. And so that is a critique of Adams' method in this example, because it's not following the quota rule. You see elsewhere it's succeeding to follow the quota rule. 42 is close to 41, 14 is close to 13.7, 20 is close to 19.76, but 137 is past 100, like 138 would be the lower end of what you would like to apportion. Now notice Hamilton's rule apportionment procedure always succeeds in this example in following the quota rule. And that's always true. Hamilton's method always follows the quota rule. And that's because of the way Hamilton's method works. It starts with the standard quota, it rounds everybody down, and then it hands out one more seat to some of the states. It never rounds down and then gives a state 2 or more seats. So with that method, you're either rounding down, so succeeding in the quota rule by rounding down, or you're adding 1 to rounding down. And adding 1 to rounding down is the same as rounding up from where you started. And so in that way, Hamilton's method always follows the quota rule. We'll find that all of the apportionment methods we have looked at so far will fail the quota rule some of the time, except for Hamilton's method. So let's write that. We can write Jefferson, Adams, Webster, and Huntington Hill can violate. Not always, will they? But they can violate the quota rule. Okay, let's look at our next way to offer critiques of apportionment methods, and that'll be called the Alabama paradox. So here's an example that we met in one of the earlier videos. So we have a county that has some social workers to distribute between 3 towns, and we're basing the apportionment on the number of cases that each town has, number of cases that a social worker would need to handle. And we're going to view it under 2 situations, one in which we apportion 24 social workers, and another in which we apportion 25 social workers. And so you can check via Hamilton's method that this will be the appropriate apportionment in each of the 2 cases. But all we want to do is check how they change from one apportionment to the next. And we want to, maybe we'll just draw some arrows to say that from 24 to 25, A lost a social worker. From 24 to 25, B gained one and C gained one. So C is the big loser here. But the reason why A is the big loser here. Let's write that. A is the loser here. But it's not just that they lost someone, because it needs to be thought of in context. They lost a social worker when more social workers were available. This is a problem. There is an interest. A has an interest in not hiring an extra worker. And that seems like a bad deal, because there shouldn't be an expectation that you might lose out if more social workers are available. And so we offer this as a critique of Hamilton's method. This is a critique of Hamilton's method. That doesn't look right. The divisor methods do not suffer from this. Do not have a chance of expressing this paradox. Express. So by the divisor techniques, I mean Jefferson's, Adams, Webster's, and Huntington Hill. They all are reliant on adjusting the divisor, so they're kind of the divisor methods. But Hamilton's method can express this, as we see in this example right here. And doesn't do it always, but it can. And so that's a critique of the method as a whole. So that's the quota rule and the Alabama paradox. In the next video, we'll talk about a couple other paradoxes. See you there.